Hello to all fans of physics, astronomy, and the exact sciences in general. This is Andrei Shetnikov with you, and we continue our series of videos about how people measured the distances to objects in deep space. And in this series, we have already made videos about how the ancient Greeks measured the size of the Earth and the distance to the Moon. Then, in the 17th and 18th centuries, the distance from the Earth to the Sun was measured. And finally, in the 19th century, the distance to the nearest stars in the solar system was determined. All of this was accomplished using geometric methods, or more precisely, the method of parallax. But once we reach the stars, to measure the distances to stars that are farther away in our galaxy, and especially to neighboring galaxies, geometric methods no longer work. The angles that need to be measured are simply too small. And so these are replaced by a method, or rather, a group of methods known as standard candles, as they are called. And today, we will be talking about the first of these methods. And this method is connected with variable stars, primarily with Cepheids. These stars are called Cepheids because they are similar to a particular variable star that astronomers designate as delta in the constellation Cepheus. And this star, according to observations, changes its brightness periodically over 5 days and 8 hours, following a curve like this, with its brightness varying by more than 1 magnitude. And it changes precisely because, as was later established, it changes its size. This is a large star. Its diameter is 40 times greater than that of the Sun. And over these 5 days and 8 hours, it increases by 4 solar diameters and then decreases, pulsating in this way. And because of this, its brightness changes. And now, on our stage, appears the remarkable American astronomer Henrietta Leavitt, who in 1908 was studying variable stars in the Small Magellanic Cloud. And Leavitt discovered that for these stars, there is a remarkable relationship between the period of their brightness variation and their maximum, and actually also their minimum brightness. And this data fits perfectly onto such a graph. And Leavitt realized that since all these stars are located at approximately the same distance from us, because the size of the Magellanic Cloud is significantly smaller than the distance to it, these data can be used to measure distances, including to other variable stars of the same type. And for this, we use the inverse square law, which states that the apparent brightness of a point source decreases in proportion to the square of the distance to it. This is because the light emission is distributed over the entire sphere surrounding the source, and the area of a sphere is proportional to the square of its radius. And here, of course, it is assumed that the light is not absorbed on its way from the source to the observer. Now, we will rely on the relationship between the period of a Cepheid variable and its peak brightness, which was discovered by Henrietta Leavitt. Let's suppose we are observing a certain Cepheid variable and see that its period is 30 days. We mark this period on the graph and determine what brightness a Cepheid with such a period would have in the Magellanic Cloud. And let's say the Cepheid we are observing is 100 times brighter at its maximum. This means we can conclude that it is 10 times closer to us than the Magellanic Cloud. And all of this works very well, except for one thing. In this scheme, we still don't know the distance to the Magellanic Cloud. Therefore, the whole project needs to be approached from a different direction. We need to find a Cepheid that is relatively close to Earth, so that its distance can be determined using the parallax method. Then, find out the period of this Cepheid. Next, compare it to the graph for the Magellanic Cloud. Determine how many times brighter it is at its maximum compared to a Cepheid with the same period in the Magellanic Cloud, and then, using this ratio of brightness, accordingly find the ratio of distances in the opposite direction. But here too there is one difficulty. The thing is, there are no Cepheids near the Earth, and the closest ones are several hundred light years away. Nevertheless, since astronomers gained the ability to look deep into space and measure distances, this project was attempted by the American astronomer Harlow Shapley in 1914, that is, 6 years after the initial result was obtained. And so, for some Cepheids within a radius of 1,000 light years around us, he measured the distance, albeit roughly. As a result, the distance to the Magellanic Cloud also became known, though with the same degree of roughness. After that, it became a matter of refining all these results. There were still many different problems. It turned out that there are two types of Cepheids, not just one, and all sorts of other things as well. But the main thing is that the principle of using standard candles is already clear from this discussion. In the next videos, we'll talk about the continuation of these methods. For now, I ask you to write your questions and comments. And thank you very much for your attention.